Hi, everyone. My name is Ala Lee. I'm a senior student from Oklahoma State University. This is a joint work with Dr. Rudra, who is an associate professor in the Department of Statistics. Our research project is investigation of the ability of normality tests to detect issues in downstream tests. The assumption of normality always needs to be checked for many statistical procedures since their validity depends on it. Violation of normality assumption in downstream tests may result in inflated type 1 error rate or loss of power. As an example showed here, the type 1 error rate for one sample t-test inflated when the data comes from a chi-square distribution. And that's the reason why usually the first step of data analysis is to test the normality using normality tests. There are different types of normality tests, and the four listed here are among the most widely used ones. The Shapiro-Wilk test is testing the null hypothesis that a sample came from a normally distributed population. The DAP test is based on transformations of the sample curtices and skewness. Both Shapiro-Wilk and the DAP tests are specifically designed to detect departures from normality. The KS test can be applied to test whether the data follow any specified distribution, not just the normal distribution. The Jerk-Bear test is testing whether sample data have the skewness and the curtices matching a normal distribution. Researchers have studied and compared the type 1 error rate and the power of normality tests under different distributions and concluded the most powerful normality test for normal and non-normal distributions respectively. We can see from the results that many of these tests have low power in smaller sample sizes. And therefore, the normality test may not be very useful when the sample size is relatively small. According to central limit theorem, in large samples where the number of observations is greater than 30, the sampling distribution tend to be normal regardless of the shape of the data. And the sample mean will themselves have a normal distribution. It implies that when the sample size is large, the need to verify normality is less. However, as we observed before, normality tests tend to show good power only when the sample size is large, in which we need them the least. And they have low power in the condition of smaller sample sizes, where verifying normality is more necessary. This is a well-known problem, but has not been extensively studied using simulations. So in our research, we are proposing a simulation framework that can be used for any test of normality and any downstream analysis that a user can use to get an idea about how the normality tests will perform for a specific downstream analysis, and the utility of the normality test in detecting issues such as inflated type 1 error or loss of power in downstream tests. The downstream test we chose first is one sample t-test. In our simulation-based research, we generated data from different distributions with varying sample sizes. The first one is chi-square distribution, which is positively skewed. And the second is beta distribution, at which we made it negatively skewed by setting parameters. And last but not least is uniform distribution, which has flat tails. And here we used Shapiro-Wilk test to estimate the power of normality test and combine it with the type 1 error rate and the power of one sample t-test to do the analysis. For chi-square distribution, we generated data with 4 different degrees of freedom and varying sample sizes. And for all the analysis, we assume 0.05 as a type 1 error rate for normal distribution and used it as a standard for the analysis. In the first plot, the y-axis is the type 1 error rate of one sample t-test. there are clear evidence of inflated type 1 error rate, will it become less problematic as the increase of sample size. And in the second plot, we use the difference of type 1 error rate between chi-square distribution and normal distribution as a y-axis. And the x-axis is the power of normality test. We can see that normality tests are somewhat useful for moderate sample sizes here. The second is beta distribution. We made the distribution negatively skewed by choosing values of parameters. And here are 4 different pairs of parameters. From the first plot, there are also evidence of inflated type 1 error rate, and it is less problematic for larger sample sizes. However, here in the second plot, we can observe that there is only very little utility of normality test in detecting issues. Last but not least, here we generated data from uniform distribution. And we found that there are both inflated type 1 error rate and loss of power in this condition. And from the plots, utility of normality tests, we can see there is still very little utility of normality tests in detecting such issues. Here we provided some possible solutions. One is to use robust statistical methods which do not require parametric assumptions. And another one is to use normality tests that are less problematic, which is also one of the aspects that we are going to explore in our future work. Our next step will mainly focus on these aspects, explore other kinds of departure of normality, explore other downstream tests, and the performance of other normality tests. Also, as mentioned before, we will attempt to find which normality tests are less problematic and more useful for a given downstream test. That's all I have for today. And if you have any recommendations or thoughts on the process, we will be very excited to hear what you have to say and what you think about all of this. So feel free to share your opinions and thoughts. Thank you so much for listening.